Right now, your body is pressing against something solid, a chair, a bed, a floor. You can feel it holding your weight. It resists your touch. But here's what physics tells us about that solid surface and about you. Every atom in your body and every atom in whatever you're sitting on is more than 99.99 recurring % empty space. If you removed all the empty space from every atom in every human being alive on Earth, all 8 billion of us, the remaining matter would fit inside a single sugar cube. So why doesn't your hand pass straight through the table? Why don't you fall through the floor right now? The answer has nothing to do with tiny hard balls packed tightly together. The real reason is far stranger, and it comes from a quantum rule that forbids certain particles from ever acting the same. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with something you do every single day without thinking about it. You touch things. You pick up a glass of water. You press your fingers against a desk. You walk across a floor and you feel it under your feet, rigid, unyielding, real. When you push on a wall, the wall pushes back. When you set a book down on a shelf, the shelf holds its weight. Matter resists matter. This seems obvious. It seems fundamental. Solidity feels like the most basic property of the physical world, the one thing you never need to question. The ground is solid. The table is solid. Your bones are solid. End of story. But physics tells us something deeply strange about every one of those objects. The glass, the desk, the wall, the book, the shelf, the floor, your bones, your skin, and every organ in your body, all of it is made of atoms. And atoms, as we now know with absolute certainty from over a century of experimental evidence, are almost entirely empty space. Not mostly empty in the way a room with sparse furniture is mostly empty. Not partially empty in the way a net has gaps between the strings. Overwhelmingly, staggeringly, almost perfectly empty. The kind of empty that makes the gaps between planets look crowded by comparison. Here is what a single atom actually looks like, structurally, based on everything physics has measured. At the center sits a nucleus, an incredibly tiny, incredibly dense knot of matter containing nearly all of the atom's mass. Surrounding that nucleus is a vast region of quantum activity, a cloud of probability where the atom's electrons exist. The nucleus is where the weight is. The electron cloud is where the size is. And the difference between the two is almost impossible to exaggerate. If you scaled up a single hydrogen atom so that its nucleus, which in hydrogen is a single proton, became the size of a basketball, the outer reaches of the electron cloud would extend roughly 6 miles away in every direction. 6 miles of nearly nothing, with a basketball sitting alone at the center. That is the internal structure of every atom in your body, in the air around you, in the ground beneath your feet. A tiny, dense core surrounded by a quantum presence that defines how large the atom appears to the outside world. This means the chair you are sitting on right now is overwhelmingly empty space at the atomic level. Your own body is overwhelmingly empty space. The floor, the walls, the ceiling, the planet itself, every solid object you have ever touched in your entire life is built from atoms that are almost entirely empty by volume. And this raises a question so basic, so fundamental, that it strikes at the heart of how we experience reality. If atoms are nearly all empty space, why does anything feel solid at all? Why doesn't your hand pass through the table? Why don't you sink through the floor and keep falling straight through the earth? The answer is one of the strangest and most beautiful explanations in all of physics. But before we can understand it, we need to understand what an atom actually is, how we discovered its bizarre internal structure, and why the picture most people carry in their heads of a tiny solar system with electrons circling a nucleus like planets orbiting a star is almost completely wrong. To do that, we need to go back roughly 2,400 years to the moment humans first asked whether matter could be divided forever or whether there was a smallest possible piece. In ancient Greece, around 400 BC, a philosopher named Democritus proposed something radical. He suggested that if you took any substance and kept cutting it in half, again and again and again, eventually you would reach a piece so small it could not be divided any further. He called these fundamental pieces atomos, a Greek word meaning uncuttable or indivisible. Democritus imagined that everything in the world, every rock, every drop of water, every breath of air, was ultimately made of these tiny, indivisible particles. Different substances had different kinds of atoms, with different shapes and sizes. But at the bottom of it all, there were building blocks that could not be broken down any further. This was purely philosophical. Democritus had no experiments, no instruments, no way to test his proposal. He was reasoning from intuition. If matter is real and physical and finite, there should be a smallest unit. You cannot divide something forever and still have something left. At some point, you reach the bottom. But another philosopher, Aristotle, disagreed entirely. Aristotle believed matter was continuous, infinitely divisible. You could always cut smaller. There was no bottom, no smallest piece, no limit to how finely you could divide a substance. And because Aristotle's intellectual influence dominated Western thought for nearly 2,000 years, the idea of atoms was pushed aside. It remained an interesting curiosity, a philosophical speculation with no real scientific standing. It took until the early 1800s for atoms to re-enter the conversation, this time not through philosophy, but through chemistry. A British scientist named John Dalton noticed something remarkable about how elements combine in chemical reactions. When hydrogen reacted with oxygen to form water, they always combined in the same ratio by mass. 8 grams of oxygen for every 1 gram of hydrogen. Always, without exception. When carbon combined with oxygen to form carbon dioxide, the ratios were similarly fixed. Every chemical reaction Dalton studied showed the same pattern. Elements combined in specific, predictable, whole number proportions. This made perfect sense if matter was made of discrete particles with specific masses. If a water molecule always consists of 2 hydrogen atoms bonded to 1 oxygen atom, and if each oxygen atom is roughly 16 times heavier than each hydrogen atom, then the fixed mass ratios follow automatically. Dalton proposed that every element is made of identical atoms unique to that element, and that chemical reactions are simply atoms rearranging into new combinations. This was powerful evidence, but it was still indirect. Nobody had seen an atom. Nobody had measured one directly. Nobody knew what atoms looked like inside, or whether they even had an inside. Atoms at this point were still a useful idea, a model that explained chemical behavior beautifully, but remained frustratingly invisible. The first real crack in the mystery came in 1897, when a British physicist named J.J. Thomson discovered something that nobody expected. He was studying cathode rays, streams of particles produced inside glass vacuum tubes when an electric current was applied. Thomson found that these rays were made of particles far smaller than any known atom. They carried negative electric charge and appeared in experiments using every element he tested, suggesting they were a universal component of all matter. Thomson called them corpuscles. We call them electrons. This was a stunning discovery. It meant atoms were not indivisible after all. They had internal structure. They contained even smaller pieces. The uncuttable building blocks of Democritus could, in fact, be cut. Something existed inside atoms, something smaller and lighter and electrically charged. Matter had a deeper layer than anyone had realized. Thomson proposed a model for the atom based on what he now knew. Since atoms are electrically neutral overall, carrying no net charge, and since they contain negatively charged electrons, there must be positive charge somewhere inside to balance things out. Thomson imagined the atom as a uniform sphere of positive charge with the tiny negative electrons scattered throughout it, like raisins embedded in a pudding. This became known as the plum pudding model. The atom was a smooth, continuous blob of positively charged material with little bits of negative charge dotted inside. It was a perfectly reasonable guess given the evidence available, and it was completely wrong. The plum pudding model survived about 14 years before it was demolished by one of the most famous experiments in the history of science. In 1911, a New Zealand-born physicist named Ernest Rutherford, along with Hans Geiger and Ernest Marsden, set up an experiment that changed everything we thought we knew about matter. They aimed a stream of alpha particles at a sheet of gold foil so thin that it was only a few hundred atoms thick. Alpha particles are helium nuclei, relatively heavy particles that carry a positive electric charge and move at high speed. If Thomson's model was correct, the alpha particles should pass through the gold atoms with only very slight deflections. The positive charge was supposed to be spread evenly throughout the atom like a smooth paste. There should be nothing concentrated or dense enough to significantly alter the path of a fast-moving particle. And for the vast majority of alpha particles, that is exactly what happened. They sailed straight through the gold foil as if it were barely there. This alone was remarkable. It meant the gold atoms were not solid barriers. Most of the atom's volume offered essentially no resistance. The alpha particles passed through empty space. But then something shocking happened. A small fraction of the alpha particles deflected at large angles. Some bounced sideways, and a tiny number, roughly 1 in 20,000, came flying almost directly backward, straight back toward the source, as if they had hit a wall. Rutherford was stunned. He later said it was as if you fired a 15-inch artillery shell at a sheet of tissue paper, and the shell came bouncing back at you. This could not be explained by a smooth, diffuse sphere of positive charge. Something inside the atom had to be unbelievably dense and concentrated, dense enough and positively charged enough to stop a fast, heavy alpha particle dead in its tracks and reverse its direction. Rutherford analyzed the mathematics of the deflection angles and concluded that virtually all of the atom's positive charge and nearly all of its mass were packed into an incredibly tiny region at the very center. He named this the nucleus. The lightweight, negatively charged electrons occupied the enormous volume of space surrounding it. The atom was not a uniform blob at all. It was almost entirely empty, with a minuscule but staggeringly dense core. The numbers involved are extreme. The nucleus of a typical atom is roughly 100,000 times smaller in diameter than the atom itself. To understand that ratio, think of it this way. An atom is typically about 1/10 of a nanometer across. A nanometer is 1/1000th of a meter. These are already almost incomprehensibly small objects. If you lined up roughly 10 billion atoms in a row, they would stretch about 1 meter, roughly the length of your arm. But the nucleus is smaller still, by a factor of approximately 100,000. If you scaled the atom up to the size of a major sports stadium, say 300 meters across, the nucleus would be sitting at the center of the field as a single, small grain about the width of a sesame seed, maybe 3 millimeters across. You could walk right past it and never notice. And the entire rest of the stadium, the seats, the hallways, the concourses, the parking lot beyond, all of it would represent space that is almost perfectly empty. Not mostly empty, not largely empty, almost perfectly empty, with a speck at the center containing nearly all the weight. That is the internal structure of every atom in the universe. Now, here is a detail that makes this even more astonishing. Despite being vanishingly small, that marble-sized nucleus contains more than 99.95% of the entire atom's mass. Almost all the weight of the atom is in the nucleus. The electrons, spread across the vast surrounding volume, contribute almost nothing to the mass. A single proton is roughly 1,836 times heavier than a single electron. A neutron is about the same. So when you hold a rock in your hand and feel its weight, that weight comes almost entirely from nuclei that collectively occupy an almost incomprehensibly small fraction of the rock's total volume. The rock feels heavy because of its nuclei. It feels large because of its electron clouds. These two properties come from entirely different places within the atom. Now, let me address something important, because this is where most people's understanding of the atom takes a wrong turn. You have almost certainly seen pictures of atoms drawn as a small cluster of coloured spheres at the centre, with smaller spheres tracing neat, circular or elliptical paths around them, like a miniature solar system. Electrons as tiny planets, the nucleus as a little sun. This is the Bohr model, named after the Danish physicist Niels Bohr, who proposed it in 1913. Bohr's model was a critical step forward in physics. It introduced the revolutionary idea that electrons can only occupy certain specific energy levels, not any arbitrary orbit. This quantization of energy was correct and important. It explained why hydrogen emits light at very specific wavelengths rather than a smooth, continuous spectrum. But the visual picture that the model planted in people's minds, electrons as little hard balls flying around the nucleus in neat, predictable paths, is deeply misleading. It is the single most common misconception about atoms, and it leads directly to confusion about why matter feels solid. Electrons do not orbit the nucleus the way the Earth orbits the Sun. They do not trace clean paths through space. They do not have well-defined positions at any given moment. If you could somehow freeze time and look inside an atom, you would not find a tiny ball at a specific point in its orbit. That picture is wrong. It is not approximately wrong or slightly simplified. It is fundamentally, structurally wrong, in a way that changes everything about how the atom actually works. What really happens inside an atom is described by quantum mechanics, the framework that governs the behavior of matter and energy at the smallest scales. In the 1920s, a revolution swept through physics. Werner Heisenberg, Erwin Schrödinger, Max Born, and others developed a mathematical framework that replaced the orbiting planet picture with something far stranger, far less intuitive, and far more accurate. In quantum mechanics, an electron in an atom does not have a definite position until it is measured. Instead, it exists as what physicists call a wave function, a mathematical description that encodes the probability of finding the electron at any given point in space. Schrödinger's equation describes how this wave function evolves over time, and Max Born interpreted its output as a probability distribution. The square of the wave function at any location gives the probability of detecting the electron there if you were to look. What does this look like in practice? If you could somehow observe a hydrogen atom, you would not see a tiny ball circling the nucleus. You would see something much more like a cloud, a diffuse, fuzzy region of probability centered on the nucleus. The cloud is densest closest to the nucleus, where the probability of finding the electron is highest, and it fades gradually as you move outward. There is no sharp edge, no hard boundary, no wall where the atom ends and empty space begins. The probability simply gets smaller and smaller, approaching zero, but technically never reaching it. This electron cloud is not a physical substance in any classical sense. It is not a mist or a gas or a fog. It is a quantum state, a mathematical description of where the electron is likely to be found upon measurement. Between measurements, the electron does not have a definite location. It is not hiding at some specific point inside the cloud, waiting to be discovered. The uncertainty is not a limitation of our instruments, it is fundamental to reality. The electron genuinely exists as a spread-out quantum state, not as a tiny particle at a secret location. This is deeply alien to everyday experience. In daily life, objects are always somewhere specific. Your phone is on the table, your car is in the driveway. A baseball is either in the air or in the glove. Things have positions. But electrons inside atoms do not have positions in that familiar sense. They have probability distributions. They are smeared across space in patterns dictated by the mathematics of quantum mechanics. The shape of the electron cloud depends on the electron's energy level and a property called angular momentum. In its lowest energy state, the hydrogen atom's electron cloud is a simple sphere centered on the proton. But higher energy states produce clouds with extraordinary shapes. Some look like dumbbells, some look like rings or toruses. Some form intricate three-dimensional patterns with lobes pointing in precise directions. These shapes are called orbitals, and they are described exactly by quantum mechanics. Each orbital has a specific energy, a specific angular momentum, and a specific spatial distribution. The mathematics predicts every detail, and every prediction matches experimental measurements with astonishing precision. This is what defines the size of an atom. Not a hard shell, not a physical wall at a fixed distance from the nucleus. The atom's size is determined by the extent of its electron cloud. When physicists say a hydrogen atom has a radius of about 53 picometers, they are describing the most probable distance at which you would find the electron in its ground state. But the cloud extends beyond that. Technically, the probability of finding the electron stretches outward indefinitely. It just becomes negligibly small at large distances. An atom does not have a crisp edge. It has a quantum boundary, a region where the probability of finding its electrons becomes vanishingly small. This is fundamentally different from any object in your everyday experience. A billiard ball has a definite surface. An atom does not. The atom fades gradually into the space around it, its electron cloud tapering off like the glow of a lantern dimming into darkness. Now let me make the full scale absolutely clear, because this is the foundation for everything that follows. Your body contains roughly 7 billion atoms. That is a 7 followed by 27 zeros. Each one of those atoms has a nucleus carrying more than 99.95% of the atom's mass, surrounded by an electron cloud that defines the atom's apparent size, but contributes almost nothing to its weight. The nucleus is about 100,000 times smaller than the full atom. So the volume of each atom is dominated by its electron cloud, a quantum probability distribution with no hard edges and no solid walls. If you took all 7 billion atoms in your body and somehow removed all the empty space, compressing every nucleus together until they were touching, the remaining matter would be smaller than a single grain of sand. The mass would be the same. You would weigh exactly what you weigh right now, but the volume would be almost nothing. Remember the claim from a moment ago that the compressed nuclear matter of every human being on Earth would fit inside a single sugar cube. That cube would weigh around 500 million metric tons, heavier than 1,000 of the tallest skyscrapers on Earth combined. Because the mass does not change when you remove the empty space. Only the volume vanishes. This is not speculation or metaphor. This is measured, confirmed, experimentally verified physics. Rutherford's gold foil experiment first revealed it in 1911, and every experiment since has refined and confirmed the picture. Particle accelerators have probed the nucleus in extraordinary detail. We know its size, we know its composition. We know that protons and neutrons inside the nucleus are themselves made of even smaller particles called quarks, bound together by the strong nuclear force carried by particles called gluons. We have measured the charge distribution inside the proton with extreme precision. All of it confirms the same basic reality. The atom is overwhelmingly empty by volume, with a tiny dense nucleus at its heart and a quantum electron cloud defining its extent. And this leads us to the question that will drive everything from here forward. You are sitting on something right now. That object is made of atoms. Your body is made of atoms. Both collections of atoms are overwhelmingly empty space. The nuclei in your body and the nuclei in the chair beneath you are separated by distances that, relative to their own size, are equivalent to miles of open emptiness. There is nothing physically blocking the nuclei in your body from passing through the enormous gaps between nuclei in the chair. And yet, you are not falling through. The chair holds your weight. Your hand cannot pass through the table. The floor supports you. Every day, in every moment, you experience a world of solid surfaces and firm boundaries, a world where matter resists matter with absolute reliability. And almost none of that resistance comes from physical objects colliding with other physical objects in any classical sense. The nuclei never touch. The electrons are not hard shells. There is no solid wall at the edge of the atom. So what is actually happening? What makes the table solid? What makes a wall impenetrable? What gives matter the resistance, the hardness, the structural rigidity that you feel in every moment of your waking life? The answer lies not in the physical substance of the atoms themselves, but in the quantum rules governing how their electron clouds interact when they get close to one another. And those rules, as we are about to discover, are far stranger, far more elegant, and far more fundamental than almost anyone outside of physics realizes. We have established something remarkable about the structure of every atom in existence. The nucleus, carrying nearly all the mass, occupies a volume roughly 1/4 of the atom's total volume. The electron cloud, carrying almost none of the mass, defines the atom's apparent size. Between the two, there appears to be nothing. But that word, nothing, is where most people's understanding goes wrong, and it goes wrong in a way that makes the question of solidity seem far more mysterious than it actually needs to be. When we talk about an atom being mostly empty space, it creates a powerful mental image. You imagine a vast, dark room with a speck at the center and a few smaller specks drifting somewhere around the edges. The room is silent. The room is vacant. The specks are so small and so far apart that the overwhelming reality of the atom seems to be nothingness, a void, an absence. This image is intuitive, it is vivid, and it is profoundly misleading. The problem is not with the scale. The proportions are real. The nucleus genuinely is about 100,000 times smaller than the full atom in diameter. The electron cloud genuinely defines a volume that is almost entirely devoid of what we would call solid material in any classical sense. These facts are not in dispute. But the word empty is doing something dangerous here. It is importing an everyday concept into a quantum situation where that concept does not apply. When you say a room is empty, you mean there is nothing in it. No furniture, no people, no objects. Just air and open floor space. The room exists as a container, and the container has nothing significant inside it. When most people hear that an atom is mostly empty space, they unconsciously apply this same picture. They imagine a container, the atom's outer boundary, with almost nothing inside it except a few particles. A tiny marble of a nucleus, a few specks of electrons, and the rest is void. But the interior of an atom is nothing like an empty room, not even close. What fills the space between the nucleus and the outer reaches of the electron cloud is not nothing. It is not a vacuum in any classical sense. It is not an absence waiting to be filled. The space inside an atom is alive with quantum activity, saturated with fields, humming with energy, and defined by probability distributions that have real, measurable, physical consequences. To understand why, we need to talk about what modern physics says about space itself. Because the idea that space can be truly empty, that you can remove everything from a region and be left with pure nothingness, turns out to be wrong. In classical physics, the physics of Newton and the everyday world, empty space was exactly that. Empty. A stage on which objects moved and forces acted, but the stage itself was inert. It had no properties of its own. It was just geometric backdrop, a coordinate system for tracking where things were and how they moved. Quantum mechanics and quantum field theory changed this completely. In the modern understanding, space is permeated by quantum fields. Not one field, but many. There is an electromagnetic field existing at every point in space. There is an electron field. There are quark fields, neutrino fields, fields associated with every fundamental particle. These fields exist everywhere, at every point, at every moment. They are the fundamental substrate of physical reality. Particles, in this framework, are not tiny hard objects floating in a void. They are excitations of these fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. A quark is a ripple in a quark field. When we say a particle exists at some location, we mean the field at that location has been excited above its ground state. When we say there is no particle at some location, we mean the field there is in its lowest energy state. But the field is still there. It never goes away. You cannot remove it. Even in the most perfect vacuum imaginable, even in a region of space where no particles exist at all, the quantum fields are still present. And because of the Heisenberg uncertainty principle, these fields cannot sit perfectly still. They fluctuate. Tiny random variations in energy bubble up and subside constantly. These fluctuations are not hypothetical. They produce real, measurable effects. The Casimir effect, predicted theoretically in 1948 and experimentally confirmed decades later, demonstrates that two uncharged metal plates placed very close together in a vacuum experience a tiny but detectable force pushing them together. This force arises entirely from quantum field fluctuations in the space between the plates. The vacuum is not empty. It has energy. It has structure. It pushes and pulls. So when we say the interior of an atom is mostly empty space, we need to be very careful about what we mean. We do not mean there is nothing there. We mean there is no concentrated mass there, no hard substance, no classical material filling the volume. But the quantum fields are present throughout. The electromagnetic field permeates the entire atom. The electron field defines the probability distribution of where the electron might be found. These fields interact, exchange energy, and create the forces that determine how the atom behaves. The electron cloud itself is the single most important structure inside the atom for understanding how matter behaves in your everyday life. It is not a passive thing. It is not a decorative haze floating around the nucleus with no real physical effect. The electron cloud is where all of the atom's external interactions happen. When one atom encounters another atom, when light strikes a surface, when chemical bonds form or break, when your hand presses against a table, all of these interactions are mediated by the electron cloud. This is because the electron cloud carries electric charge. Electrons are negatively charged particles, and even though the electron in a hydrogen atom exists as a spread-out probability distribution rather than a tiny ball at a specific location, that probability distribution still carries the electron's full negative charge. The charge is distributed across the cloud, denser where the probability of finding the electron is higher, thinner where it is lower. But the total charge is always exactly the charge of one electron. This distributed charge creates an electric field that extends outward from the atom. Other charged particles respond to this field. Other atoms respond to this field. The electron cloud is not passively occupying space. It is actively broadcasting its presence to the surrounding environment through the electromagnetic force, one of the four fundamental forces of nature, and by far the most relevant one for understanding why matter feels solid. The electromagnetic force is extraordinarily powerful at atomic scales. It is the force between electric charges, and it governs almost everything you experience in daily life. When you touch something, you are experiencing the electromagnetic force. When you see color, you are detecting electromagnetic radiation. When a chemical reaction occurs, electromagnetic forces between electrons rearrange atomic bonds. The hardness of diamond, the softness of silk, the elasticity of rubber, the brittleness of glass. Every single one of these material properties arises from electromagnetic interactions between electron clouds. To appreciate why the electromagnetic force matters so much for solidity, consider its strength compared to gravity. Gravity is the force you are most familiar with. It holds you to the ground. It keeps the Earth in orbit around the Sun. It shapes galaxies and governs the large-scale structure of the universe. Gravity seems powerful, but at the atomic level, gravity is almost comically weak compared to electromagnetism. How weak? If you compare the electromagnetic force between two protons to the gravitational force between those same two protons at the same distance, electromagnetism is stronger by a factor of roughly 10 to the 36. That is a 1 followed by 36 zeros. The electromagnetic force between two protons is about a trillion times stronger than the gravitational force between them. Gravity is completely irrelevant at atomic scales. It contributes nothing measurable to how atoms interact with each other. When your hand presses against a table and the table pushes back, gravity plays no role whatsoever in that resistance. The resistance is entirely electromagnetic. Now let us see what happens when two atoms approach each other. This is where the story of solidity really begins. Imagine two hydrogen atoms drifting toward one another in space. Each atom has a single proton as its nucleus, and a single electron existing as a probability cloud around that nucleus. Each atom, viewed from the outside, is electrically neutral. The positive charge of the proton exactly cancels the negative charge of the electron. So from a distance, neither atom exerts much electromagnetic force on the other. They drift closer without significant interaction. But as the atoms get nearer and their electron clouds begin to overlap, something changes. The electron clouds are negatively charged. When two negatively charged regions of space begin to occupy the same volume, they repel each other. Like charges repel. This is one of the most fundamental rules of electromagnetism, established experimentally over 2 centuries ago and confirmed in every experiment since. The repulsion is not gentle. As the electron clouds overlap more and more, the repulsive force climbs steeply. The closer the atoms are pushed together, the more their electron clouds are forced into the same region of space, and the stronger the electromagnetic repulsion becomes. This creates a powerful force that pushes the atoms apart, resisting any attempt to squeeze them closer together. But repulsion is only half the story of how atoms interact at close range. If atoms did nothing but repel each other whenever they got close, matter would never form at all. There would be no molecules, no solids, no liquids, no chemistry. Every atom would push every other atom away, and the universe would be nothing but a diffuse gas of isolated atoms drifting through space, never bonding, never combining, never building anything. Something else must also be happening, and it is. At certain distances, atoms actually attract each other. This attraction arises because the electron cloud of one atom can interact favorably with the nucleus of another atom, and vice versa. Remember, the nucleus is positively charged and the electron cloud is negatively charged. When two atoms are at moderate separations, not overlapping but not far apart, the negative electron cloud of each atom is attracted to the positive nucleus of the other. This creates a net attractive force pulling the atoms toward each other. The strength and character of this attraction vary enormously depending on the atoms involved and how their electron clouds interact. Some atoms share electrons with each other. Some transfer electrons entirely, creating charged ions that attract through electrostatic force. Some interact only through fleeting fluctuations in electron density that create momentary attractions between otherwise neutral atoms. The mechanisms differ, but the outcome is the same. At moderate distances, atoms pull toward each other. The electromagnetic force that will repel them at very close range is the same force that attracts them at slightly longer range, depending on how the charges are arranged. In every case, the attractive force pulls atoms closer together. But as the atoms get closer and their electron clouds begin to overlap significantly, the repulsive force we already discussed kicks in. The negatively charged electron clouds repel each other, and the Pauli exclusion principle, which we will explore in depth shortly, prevents the electrons from accommodating the compression by dropping into the same quantum states. This creates a competition. At large distances, the atoms barely interact. As they approach, the attractive force grows, pulling them together. But as they get even closer, the repulsive force grows faster than the attractive force. Eventually, the two forces balance. There is a specific distance at which the attraction pulling the atoms together exactly equals the repulsion pushing them apart. This distance is the equilibrium bond length. It is the natural separation at which two bonded atoms settle. For two hydrogen atoms forming a hydrogen molecule, the equilibrium bond length is about 74 picometers, roughly 3/4 of an angstrom. For two carbon atoms in a diamond lattice, it is about 154 picometers. For two oxygen atoms in an oxygen molecule, it is about 121 picometers. Each pair of elements, each type of bond, has its own specific equilibrium distance, determined entirely by the balance between electromagnetic attraction and quantum mechanical repulsion. Push the atoms closer than this equilibrium distance, and the repulsive force dominates, pushing them back. Pull them farther apart, and the attractive force dominates, pulling them together. The equilibrium point is stable. The atoms sit in an energy well, a valley in the energy landscape. Pushing them in either direction requires energy. They resist being moved from their equilibrium position and snap back when released, like a ball resting at the bottom of a bowl. This is profoundly important for understanding solidity. When you touch a solid object, you are encountering atoms that are sitting at their equilibrium bond lengths, settled into the bottom of their energy wells. When you push on the surface, you are trying to compress those bonds, to push atoms closer together than their equilibrium distance. The repulsive force rises steeply, pushing back against your hand. The harder you push, the more the bonds are compressed, and the more powerfully the electromagnetic repulsion resists. This is why solid surfaces feel rigid. You are pushing against the steep, repulsive wall of billions upon billions of energy wells simultaneously. Now think about what happens at the surface of a solid object, the place where your hand actually meets the table. The atoms at the surface of the table are bonded to atoms beneath them, sitting at equilibrium distances within the material. But the surface atoms have no bonding partners above them. Their electron clouds face outward into the air, unbonded and available to interact with whatever approaches. When the atoms on the surface of your skin approach the atoms on the surface of the table, the electron clouds begin to interact. At these very close separations, the interaction between two surfaces that are not chemically bonding with each other is dominated by the repulsive side of the energy curve. The surface atoms of your skin and the surface atoms of the table are not sharing electrons. They are not forming bonds. They are simply two collections of negatively charged electron clouds being forced into close proximity, and the electromagnetic repulsion between those clouds rises steeply. This repulsion is what you feel as resistance. The table pushes back against your hand because you are trying to push the electron clouds at the table's surface closer to the electron clouds at your skin's surface than the steep repulsive wall of the electromagnetic interaction allows. You are pushing against the side of an energy well, and the well pushes back. The equilibrium bond lengths within a material also determine how dense that material is. Materials with short bond lengths pack atoms more tightly and tend to be denser. Materials with longer bond lengths have more space between nuclei and tend to be less dense. The bond length sets the spacing. The spacing determines the density. The density contributes to how the material feels in your hand, how much a given volume of it weighs, how sound travels through it, how it responds to heat. All of it traces back to the equilibrium distance between atoms, the distance where electromagnetic attraction and quantum repulsion reach a perfect, stable balance. At the same time, the positively charged nuclei of the two atoms begin to repel each other as well. Protons repel other protons. As the atoms are pushed closer and their nuclei get nearer, this nuclear repulsion adds to the resistance. But in everyday situations, the electron clouds interact long before the nuclei get anywhere close to each other. The electron clouds extend far beyond the nuclei, and their mutual repulsion kicks in at much larger separations. The nuclei never come close to touching under normal conditions. They are shielded by the enormous intervening volume of the electron clouds. This is a crucial point, and it deserves emphasis. When you press your hand against a table and feel resistance, you are not feeling nuclei colliding with nuclei. The nuclei in your hand and the nuclei in the table are never anywhere near each other. They are separated by distances that, relative to their own size, are vast. What you are feeling is the electromagnetic repulsion between trillions upon trillions of electron clouds in the atoms of your skin being pushed against trillions upon trillions of electron clouds in the atoms of the table surface. Let me walk you through this in detail, because it is one of the most remarkable things happening in your life at every single moment, and you have never once been aware of it. Your hand is made of atoms, mostly carbon, hydrogen, oxygen, and nitrogen, with smaller amounts of other elements. These atoms are arranged into molecules. The molecules are organized into cells. The cells form tissues, and the tissues form the skin on the surface of your hand. At the atomic level, the outermost layer of your skin consists of atoms whose electron clouds face outward. These electron clouds are the interface between your body and the outside world. The table is also made of atoms, maybe wood, which is primarily carbon, hydrogen, and oxygen arranged in cellulose fibers, maybe metal, with atoms arranged in a crystalline lattice, maybe glass, with silicon and oxygen atoms locked in an amorphous structure. Whatever the material, the surface of the table consists of atoms whose electron clouds face upward toward your hand. When you place your hand on the table and push down, the electron clouds on the bottom of your hand approach the electron clouds on the top of the table. As these clouds get close, within a few angstroms of each other, the electromagnetic repulsion between them increases dramatically. This repulsion pushes upward on your hand and downward on the table. At equilibrium, the repulsive force exactly balances the downward force your muscles are applying. Your hand stops moving. You feel the table resisting your push. The table feels solid. But what has actually happened at the atomic level is that the electron clouds of two vast collections of atoms have gotten close enough to repel each other electromagnetically, and that repulsion has halted your hand's motion. No solid surface has made contact with another solid surface, because there are no solid surfaces at the atomic level. There are only electron clouds interacting through the electromagnetic force. This is true for every experience of physical contact you have ever had. Every time you have shaken someone's hand, you were not touching them. Your electron clouds interacted with their electron clouds through electromagnetic repulsion. Every time you have picked up an object, your fingers did not make contact with the object in any classical sense. The electron clouds in your fingerprint ridges repelled the electron clouds on the object's surface, creating enough friction and normal force for you to grip it. Every time you have walked across a floor, you were not touching the floor. You were hovering above it, suspended by electromagnetic repulsion between the electron clouds in the soles of your shoes and the electron clouds in the floor's surface. The gap is inconceivably small. We are talking about fractions of a nanometer, distances so tiny that they are utterly imperceptible to your senses. But the gap is real. There is always a space between the atoms of your body and the atoms of everything you interact with. That space is maintained by the electromagnetic force between electron clouds. You have never truly touched anything in your life in the sense of making atom-to-atom nuclear contact. No human being ever has. It is physically impossible under normal conditions. Now let me give you a sense of just how much electromagnetic activity is happening every time you feel something solid. When you press your palm flat against a table, the contact area might be roughly 80 square centimeters. Within that area, on both your skin surface and the table's surface, there are enormous numbers of atoms. Tens of quadrillions of atoms at each surface, each with its own electron cloud, each interacting electromagnetically with the electron clouds nearby. The total number of individual electromagnetic interactions happening in the region where your hand meets the table is staggering. Countless tiny repulsive forces, all acting in concert, all pushing in the same general direction, all adding up to produce the single macroscopic sensation you experience as the table is solid and my hand cannot pass through it. This is why solidity feels so absolute, so binary. Your hand either passes through something or it does not. A surface either holds your weight or it breaks. There is no gradual transition between solid and not solid in your everyday experience. This is because the electromagnetic repulsion between electron clouds ramps up extremely steeply as atoms get close together. There is a distance at which two atoms barely interact at all, and a slightly shorter distance at which the repulsion becomes enormously powerful. The transition zone is incredibly narrow, just a fraction of an atomic diameter. So from your perspective, with fingers that are millions of atoms wide, the boundary between solid and not solid feels perfectly sharp. You either push through or you do not. This also explains something that might seem obvious, but is actually deeply revealing about the role of electron clouds. Different materials have different hardnesses. Diamond is one of the hardest natural substances known. Talc is one of the softest minerals you can find. Both are made of atoms. Both are mostly empty space at the atomic level. Both are held together entirely by electromagnetic forces between electron clouds. And yet one can scratch almost any surface on Earth while the other crumbles between your fingers. The difference has nothing to do with what the atoms are. It has everything to do with how the electrons around those atoms are arranged. The number of bonds each atom forms, the directions those bonds point, how strongly the shared electrons are held, and whether the resulting structure extends rigidly in 3 dimensions or separates into layers that slide apart. All of this depends on the quantum configuration of the electron clouds. Change the configuration and you change the material entirely, even if the atoms are identical. This principle governs everything around you. The reason some substances are hard and others soft, some rigid and others flexible, some transparent and others opaque, is not because they are made of fundamentally different stuff. It is because the electron clouds in those substances are organized differently. The electromagnetic interactions between those electron clouds, shaped by the quantum states available to the electrons, produce different architectures at the atomic level. Those different architectures scale up into the different material properties you experience with your hands and eyes. Think about a copper wire and a ceramic tile sitting side by side on a table. Both are made of atoms. Both are mostly empty space. Both derive their structural integrity from electromagnetic interactions between electron clouds governed by quantum rules. And yet, one bends smoothly in your hands, while the other shatters when dropped on a hard floor. Same physics, same fundamental forces, completely different behavior. The difference is entirely in how the electrons are organized, which bonds they form, how freely those electrons can move, and how the quantum architecture of each material responds when force is applied. We will explore exactly how this works shortly, material by material. But for now, the essential point is this. Every material property you can name, hardness, elasticity, brittleness, conductivity, transparency, color, all of these are determined by the arrangement and behavior of electron clouds. The electron cloud is not a minor detail of atomic structure. It is the part of the atom that determines how matter looks, feels, and behaves. The nucleus provides the mass and the positive charge that holds the electron cloud in place. But the electron cloud provides everything else. Everything you experience about the material world around you, its textures, its colors, its resistance to your touch, is a consequence of how electron clouds are arranged and how they interact with each other and with light. This is why the concept of emptiness inside an atom is so misleading. Yes, the atom's volume is not filled with dense material. Yes, the nucleus is tiny compared to the full atom. But the electron cloud that fills the remaining volume is not nothing. It is a quantum state carrying electric charge, creating electromagnetic fields, and governing every interaction the atom has with the outside world. Calling the interior of an atom empty is like calling the ocean empty because it is transparent. There is no solid material between you and the seafloor when you look through clear water, but the ocean is anything but empty. It is full of water, and that water has mass, energy, pressure, and physical consequences. The electron cloud has a similar character. You cannot see it, you cannot touch it in any classical sense, but it carries charge, exerts forces, and determines how matter behaves. So, now we have the first piece of the puzzle. When you press your hand against a table and feel it resist, the immediate cause of that resistance is electromagnetic repulsion between electron clouds. Your electron clouds push against the table's electron clouds, and the fundamental electromagnetic force between like charges pushes them apart. The nuclei never get close to each other. The electrons are not forming a hard wall. Instead, the repulsion is a continuous electromagnetic interaction between charged quantum probability distributions, increasing in strength as the distance decreases. But here is something important. Electromagnetic repulsion between electron clouds is not the whole story. If it were, there would be a deep problem. Consider what happens when you compress a material under enormous force. You squeeze it, pushing the atoms closer and closer together. The electron clouds resist being compressed because of electromagnetic repulsion. This is true, and it accounts for much of the everyday experience of solidity. But in extreme situations, like inside a collapsing star, where gravity crushes matter with almost inconceivable power, the gravitational force pressing atoms together becomes enormously strong, far more powerful than anything you could ever exert with your hands or any machine on Earth. Under such extreme pressure, electromagnetic repulsion alone would eventually be overcome. The atoms would be crushed closer and closer together, the electron clouds overlapping more and more, the electrons losing the space they normally occupy. If electromagnetic repulsion were the only thing preventing collapse, there would be nothing stopping the electrons from simply being squeezed into lower and lower energy states, all of them falling toward the lowest energy level, occupying the same tiny volume around the nucleus, and the material collapsing into a state far denser than any normal solid. But they do not collapse. They cannot. And the reason they cannot is not electromagnetic. It is something far more fundamental. It is a quantum mechanical rule so absolute, so non-negotiable, that it shapes the structure of every atom, every molecule, and every solid object in the universe. Without it, matter as we know it would not exist. Chemistry would not work. Stars would not shine the way they do. You would not exist. This rule has a name. It is called the Pauli exclusion principle, and it is the second, and perhaps more profound, reason why matter is solid. It is the hidden foundation beneath every surface you have ever touched, every wall that has ever stopped you, every floor that has ever held your weight. The Pauli exclusion principle is one of those ideas in physics that sounds modest when you first hear it stated. It sounds like a technical detail, a footnote buried somewhere in the machinery of quantum mechanics that only matters to specialists. But it is not a footnote. It is arguably the single most important rule governing the structure of matter in the universe. Without it, atoms would not have the structure they have. The periodic table of elements would not exist. Chemistry would not work. Stars would collapse in ways they do not. And solidity, the property that lets you stand on a floor and sit in a chair and hold a cup of coffee without your fingers passing through the handle, would simply not exist. The universe without the Pauli exclusion principle would be unrecognizable. It might not even be a universe that contains anything we would call matter. To understand this rule, we need to talk about a quantum property that has no equivalent in the everyday world. It is called spin. Spin is one of the most counterintuitive concepts in all of physics. When physicists discovered it in the 1920s, they gave it a name borrowed from everyday experience, because the mathematics resembled the mathematics of rotation. An electron has spin, and in some formal mathematical sense, this spin behaves like angular momentum, the quantity that describes how quickly something rotates and how hard it is to stop that rotation. A spinning top has angular momentum. A planet rotating on its axis has angular momentum. The mathematics describing electron spin uses similar equations. But here is the critical thing. The electron is not actually spinning. It is not a tiny ball rotating on an axis. Remember, as far as any experiment has ever been able to determine, an electron has no physical size at all. It behaves as a point particle. It has no surface. It has no equator. There is nothing to spin in the classical sense. And yet the electron possesses this intrinsic property called spin, a built-in angular momentum that it carries at all times. A quantum mechanical property that has no classical analogue and no everyday equivalent. It is simply a feature the electron has, like its charge and its mass. It was not added later. It was not acquired through some process. It is fundamental. The spin of a particle is measured in units related to Planck's constant, and it comes in specific quantized values. Electrons have a spin of 1/2. Protons have a spin of 1/2. Neutrons have a spin of 1/2. These particles all share the same spin value. Other particles have different spins. Photons, the particles of light, have a spin of 1. The hypothetical graviton would have a spin of 2. Certain exotic particles have spins of 0, 3/2, or higher values. This might sound like a dry catalogue of numbers, but these numbers divide every particle in the universe into two fundamentally different categories, and this division has consequences more profound than almost anything else in physics. Particles with half-integer spin, meaning spin 1/2, 3/2, 5/2, and so on, are called fermions. Electrons are fermions. Protons are fermions. Neutrons are fermions. Quarks are fermions. These are the particles that make up matter. Everything you have ever touched, everything you have ever seen, everything your body is made of, is built from fermions. Particles with integer spin, meaning spin 0, 1, 2, and so on, are called bosons. Photons are bosons. Gluons, which carry the strong nuclear force, are bosons. The Higgs boson, discovered at the Large Hadron Collider in 2012, is a boson. These are the particles that typically carry forces, mediating interactions between fermions. The naming convention reflects the physicists who worked out the statistical behavior of each type. Fermions are named after Enrico Fermi. Bosons are named after Satyendra Nath Bose. Paul Dirac contributed foundational work to understanding both categories. The mathematics describing how large collections of fermions behave is called Fermi-Dirac statistics. The mathematics describing bosons is called Bose-Einstein statistics. These are different statistical frameworks because fermions and bosons behave in fundamentally different ways when placed together in groups. And this is where the Pauli exclusion principle enters. In 1925, an Austrian physicist named Wolfgang Pauli discovered a rule governing fermions that has no equivalent for bosons. The rule is simple to state, but staggering in its consequences. No two identical fermions can occupy the same quantum state at the same time. That is the entire rule, one sentence. But let me unpack what it means, because the words quantum state carry enormous weight. A quantum state is a complete description of a particle's condition. For an electron in an atom, the quantum state includes its energy level, its orbital shape, its orientation in space, and the direction of its spin. If two electrons have identical energy, identical orbital shape, identical orientation, and identical spin direction, they are in the same quantum state. And the Pauli exclusion principle says this is forbidden. It cannot happen. It is not merely unlikely or difficult to achieve, it is absolutely impossible. The laws of quantum mechanics prohibit it in the most fundamental way. This rule applies only to fermions. Bosons face no such restriction. You can pack as many photons as you want into the same quantum state. Lasers work precisely because enormous numbers of photons are coaxed into occupying the same quantum state simultaneously, producing coherent light. Bosons are social. They are happy to pile up, to share, to occupy the same condition as their neighbors. There is no limit to how many bosons can be in the same state at the same time. Fermions are the opposite. They are absolutely, uncompromisingly exclusive. Each fermion demands its own unique quantum state. No sharing, no exceptions. No circumstances under which this rule is violated. It holds everywhere in the universe, at all times, under all conditions, from the interior of a collapsing star to the atoms in a blade of grass. The immediate and most visible consequence of the exclusion principle is the structure of the atom itself. This is something you may have encountered in chemistry class. Electrons in atoms are arranged in shells and subshells, each with a specific capacity. The first shell can hold at most 2 electrons. The second shell can hold at most 8. The third can hold 18. This arrangement, which gives rise to the periodic table and determines the chemical behavior of every element, is a direct consequence of the Pauli exclusion principle. Here is why. Each shell corresponds to a specific energy level. Within each shell, there are subshells with different orbital shapes. Within each subshell, there are orbitals with different spatial orientations. And each individual orbital can hold at most 2 electrons, because an electron can spin in one of 2 directions, up or down, and those 2 spin states are different quantum states. 2 electrons in the same orbital with opposite spins have different quantum states, so the exclusion principle allows both. But a third electron cannot join them. There is no third spin direction. The orbital is full. Any additional electron must go to a different orbital, a different subshell, or a different shell entirely. This is why atoms have the structures they do. This is why carbon behaves differently from oxygen, why iron behaves differently from gold, why helium is inert while sodium is violently reactive. The chemical properties of every element depend on how many electrons it has and how those electrons are arranged in shells and subshells. And that arrangement is dictated entirely by the exclusion principle. Remove the rule, and every electron in the atom would fall to the lowest possible energy state. Every atom would have the same structure. Chemistry would not exist. There would be no periodic table. There would be no molecules. There would be no you. Now let us connect this to the question of solidity, because this is where the exclusion principle does something truly extraordinary. We established earlier that electromagnetic repulsion between electron clouds is the first mechanism that makes matter resist compression. When you push your hand against a table, the negatively charged electron clouds repel each other, and this electromagnetic force prevents the atoms from interpenetrating. This is real and important, and accounts for much of the everyday experience of solidity. But the exclusion principle adds a second mechanism, one that operates at a deeper level and that becomes dominant under extreme conditions. This mechanism is called degeneracy pressure, and it is purely quantum mechanical. It has no classical equivalent. Nothing in Newtonian physics, nothing in everyday experience, nothing in your intuitive understanding of how forces work can prepare you for it. It is a consequence of quantum statistics and the exclusion principle, and it exists even when there are no conventional forces pushing atoms apart. Here is how it works. Imagine compressing a collection of atoms, pushing them closer and closer together. As the atoms get closer, their electron clouds begin to overlap. The electrons from different atoms start sharing the same region of space. Now, the exclusion principle kicks in. Each electron must be in a unique quantum state. When the available space shrinks, the number of low-energy quantum states available in that space decreases. The electrons cannot all occupy the lowest energy states because there are not enough distinct low-energy states to accommodate all of them. So what happens? The electrons are forced into higher and higher energy states. Some electrons must occupy states with more energy, more momentum, and more kinetic activity than they otherwise would. These high-energy electrons exert outward pressure. They are moving faster and carrying more momentum than they would in an unconstrained system. This outward pressure, arising entirely from the fact that electrons cannot share quantum states, resists further compression. This is degeneracy pressure. It is not caused by heat. It is not caused by electromagnetic repulsion. It is not caused by any conventional force. It arises purely and entirely from the Pauli exclusion principle, from the quantum mechanical requirement that fermions must each occupy a unique quantum state. Even if you cooled the material to absolute zero, removing all thermal energy, the degeneracy pressure would remain. It is irreducible. It is a direct consequence of quantum mechanics, and it provides a floor of resistance beneath which matter cannot be compressed without violating a fundamental law of physics. In everyday life, you do not notice degeneracy pressure as a separate phenomenon because it operates alongside and beneath the electromagnetic repulsion between electron clouds. Both effects contribute to the rigidity of the table, the firmness of the ground, the resistance you feel when you push on any solid surface. But degeneracy pressure is there, quietly doing its work at the quantum level, preventing the electrons in matter from all collapsing into the same low-energy state and allowing the material to crumble into a uniform, featureless blob. To see degeneracy pressure at its most dramatic, we need to leave ordinary matter behind and look at one of the most extreme objects in the universe, a white dwarf star. A white dwarf is what remains after a star like our Sun exhausts its nuclear fuel and dies. During its life, such a star burns hydrogen in its core through nuclear fusion, converting it into helium and releasing enormous amounts of energy. This energy creates outward pressure that balances the inward pull of gravity, keeping the star stable. But eventually, the fuel runs out. The star can no longer sustain fusion at a rate sufficient to hold itself up. Gravity wins. The outer layers of the star are expelled into space, forming a beautiful glowing shell called a planetary nebula. What remains is the core, a dense ball of matter about the mass of the Sun, compressed into a volume roughly the size of the Earth. This is the white dwarf. Think about that for a moment. The mass of our entire Sun, which is roughly 330,000 times more massive than Earth, squeezed into a sphere no larger than our planet. The density is staggering. A teaspoon of white dwarf material would weigh roughly 5 metric tons on Earth. 5 metric tons in a teaspoon. That is denser than anything you will ever encounter in everyday life by a factor of millions. Under these conditions, the atoms have been crushed together until their electron clouds have completely overlapped. The material is no longer made of distinct atoms with separate electron clouds. The electrons have been liberated from individual nuclei and form a dense, compressed sea of electrons pervading the entire star. The nuclei are packed closely together, immersed in this electron sea. Now, what prevents this incredibly dense ball of matter from collapsing further? Gravity is immense. The weight of the overlying material presses inward with colossal force. And yet, the white dwarf holds its shape. It does not collapse into a point. It does not shrink further. Something is holding it up. That something is electron degeneracy pressure. The electrons in the white dwarf cannot all fall into the lowest energy state. The Pauli exclusion principle forbids it. Each electron must occupy a unique quantum state, and in such a compressed volume, the number of available low-energy states is severely limited. Vast numbers of electrons are forced into high-energy, high-momentum states. These high-energy electrons create tremendous outward pressure, a pressure that owes nothing to heat, nothing to electromagnetic repulsion between individual atoms, and nothing to nuclear fusion. It is pure quantum mechanical resistance, arising entirely from the exclusion principle. This pressure is strong enough to support the entire mass of a dead star against gravitational collapse. An object as massive as the Sun, crushed to the size of a planet, held up not by any force in the conventional sense, but by a quantum rule that says fermions cannot share quantum states. This is extraordinary. It means the Pauli exclusion principle is not just a detail of atomic physics. It is powerful enough to hold up a star. The Indian-American astrophysicist Subramanian Chandra Shekhar worked out the mathematics of this in the early 1930s, when he was only about 20 years old. He calculated that electron degeneracy pressure can support a white dwarf only up to a certain mass limit, roughly 1.4 times the mass of the Sun. Beyond that limit, gravity overwhelms even the exclusion principle's resistance. The electrons are forced to combine with protons, producing neutrons and releasing neutrinos. The star collapses further. This mass limit is called the Chandrasekhar limit, and it was one of the most important discoveries in 20th century astrophysics. Sirius B, the companion star to Sirius, the brightest star in our night sky, is a white dwarf. It has about the mass of our Sun, packed into a volume roughly the size of Earth. It is held up entirely by electron degeneracy pressure. It has no fusion reactions generating energy. It has no thermal pressure in the usual sense holding it up. It is slowly cooling, radiating away the heat it accumulated during its life as a normal star, and it will eventually fade to a cold, dark cinder over trillions of years. But for all that time, it will maintain its size, because the Pauli exclusion principle will never stop operating. The quantum rule that forbids electrons from sharing states will hold the dead star up for as long as matter exists. Now, what happens when the Chandrasekhar limit is exceeded? When a stellar core is more massive than roughly 1.4 solar masses, and gravity crushes the electrons past the point where even degeneracy pressure can resist, the electrons are forced into the protons. Each electron combines with a proton to produce a neutron and a neutrino. The neutrinos escape. What remains is a ball of neutrons, an object so dense it defies imagination. This is a neutron star. A neutron star might contain 1.5 to 2 times the mass of the Sun, compressed into a sphere roughly 12 miles across. 12 miles. That is about the width of a mid-sized city. The entire mass of a star larger than our Sun squeezed into a space you could drive across in 20 minutes. The density is beyond anything in ordinary experience. A teaspoon of neutron star material would weigh roughly 4 billion metric tons. And what holds up a neutron star against further gravitational collapse? Neutron degeneracy pressure. The same Pauli exclusion principle, now applied not to electrons but to neutrons, which are also fermions with spin 1/2. The neutrons cannot all occupy the same quantum state. They are forced into higher energy states, creating immense outward pressure that resists gravity. The principle is identical, only the particles are different. Neutron degeneracy pressure holds up neutron stars against gravitational forces so extreme that they would crush any ordinary material into nothingness. And yet, even neutron degeneracy has a limit. If the mass exceeds roughly 2 to 3 solar masses, depending on the details of neutron interactions, which remain an active area of research, gravity wins again. Nothing can prevent further collapse. The result is a black hole, a region of space-time where gravity is so intense that not even light can escape. At that point, the quantum rules that held matter together through every previous stage of compression have finally been overwhelmed. But for all the matter you interact with in your daily life, for every solid surface and every physical object you will ever encounter, the situation never approaches these extremes. And yet, the exclusion principle is working. It is always working. It operates in the atoms of your body right now. It operates in the chair beneath you, in the floor below that, in the walls around you. It determines how electrons are distributed in every atom. It shapes every chemical bond. It creates the electron shell structure that gives elements their properties. And it provides a fundamental quantum resistance to compression that underlies the solidity of every object you have ever touched. Let me be absolutely clear about what this means for the central question of why matter is solid. Solidity does not come from physical contact between dense objects packed tightly together. You might imagine the atoms in a table as tiny billiard balls jammed side by side, each one solid, each one pressing firmly against its neighbours. But that picture is entirely wrong. The dense part of each atom, the nucleus, occupies roughly 1/4 of the atom's total volume. There is nothing hard at the atom's outer boundary. There is no shell, no wall, no crust. The boundary of every atom is a quantum probability distribution that fades gradually into the space around it. What creates the resistance is not hard objects in contact, it is the quantum behavior of the electron clouds that defines those boundaries. What there is, instead, is a combination of two quantum phenomena working together. First, the electromagnetic repulsion between negatively charged electron clouds, which pushes atoms apart as they approach each other. And second, the Pauli exclusion principle, which prevents the electrons in those clouds from simply collapsing into the same low-energy quantum states, creating degeneracy pressure that resists compression at a fundamental level. These two mechanisms operating together create the phenomenon we call solidity. Neither one alone is sufficient. Electromagnetic repulsion explains why atoms resist being pushed together at moderate pressures. The exclusion principle explains why matter has a fundamental structural rigidity that persists even under extreme conditions, why electrons maintain their shell structure, and why atoms have the definite sizes and shapes that allow them to form stable molecules and materials. Without the electromagnetic force, electrons would not repel each other as atoms approached, and matter would have no resistance to compression at ordinary scales. Without the exclusion principle, electrons would all pile into the lowest energy state. Atoms would have no shell structure, no definite size, no chemical properties, and matter would not form the rigid, textured, diverse world of materials that you experience every day. Both mechanisms are essential. Both operate simultaneously, and both are quantum mechanical in origin. The world feels solid not because it is made of solid things at the smallest scale, but because quantum rules governing the behavior of electrons create effective rigidity at the scale of atoms and molecules, which then scales up to produce the hardness, texture, and structural integrity of every macroscopic object in your daily life. The chair beneath you is held up by quantum mechanics. The ground under your feet is rigid because of quantum mechanics. The walls of your house resist your push because of quantum mechanics. Every surface you have ever touched, every object you have ever held, every floor you have ever walked across, all of it derives its solidity from quantum rules operating at scales far too small to see, creating an illusion of solid continuous matter from particles that are not solid, structures that have no hard edges, and atoms that are overwhelmingly empty. This is one of the most profound realizations in all of physics. The tangible, resistant, unyielding physical world you inhabit every moment of every day is built entirely from quantum phenomena that operate in a realm no human sense organ can access. You experience the consequences of these phenomena constantly, in every physical interaction, with perfect reliability and absolute consistency. But the mechanisms producing those consequences are invisible, counterintuitive, and fundamentally unlike anything in your everyday experience. And as we are about to see, these mechanisms do not merely explain why you cannot push your hand through a table. They explain why the world has texture, why some things are hard and others soft, why metals conduct electricity and glass does not, why diamond sparkles and graphite crumbles. The quantum rules that make matter solid are the same rules that determine why diamond cuts glass, why copper carries current, why rubber stretches and snaps back, and why bone can support your weight without shattering. We have identified the mechanisms. Now it is time to see them at work, building the actual world you live in, one material at a time. We have arrived at the heart of the matter, We know the two mechanisms. We know that electromagnetic repulsion between negatively charged electron clouds pushes atoms apart as they approach each other. And we know that the Pauli exclusion principle, the quantum rule forbidding identical fermions from occupying the same quantum state, prevents electrons from collapsing into the lowest energy configuration and creates a fundamental resistance to compression called degeneracy pressure. These two effects working together produce the phenomenon we experience as solidity. But knowing the mechanisms is not enough. The question that remains is how. How do rules operating at the scale of individual atoms, at distances measured in billionths of a meter, create the world you actually live in? How do quantum probability distributions and exclusion rules produce a floor that holds your weight, a wall that stops your hand, a knife edge that cuts, a rubber ball that bounces, and a glass window that shatters? How does the quantum become the tangible? The answer is scale. Scale and repetition. A single atom interacting with another single atom through electromagnetic repulsion and exclusion-based rigidity produces an almost immeasurably tiny force. The interaction between two hydrogen atoms as their electron clouds begin to overlap generates a repulsive force that, measured in everyday units, rounds to zero. It is fantastically small. No human sense organ could ever detect it. No instrument you hold in your hand could measure it directly. But you are not made of two atoms. Your hand alone contains roughly 10 trillion atoms. That is a 1 followed by 25 zeros. Every one of those atoms has an electron cloud. Every one of those electron clouds is interacting electromagnetically with the electron clouds of neighboring atoms. And every one of those interactions is governed by the exclusion principle, which dictates how electrons are distributed across quantum states. When you press your hand against a table, you are initiating an almost inconceivable number of simultaneous quantum interactions at the surface of contact. Thousands of trillions of atoms on each surface, each with its own electron cloud, each generating electromagnetic repulsion against the electron clouds facing it from the other side. Each interaction is tiny, each one is invisible, but they are all pushing in the same direction, all resisting the same compression, all obeying the same quantum rules. The cumulative effect of thousands of trillions of tiny electromagnetic repulsions, backed by the structural rigidity imposed by the exclusion principle, is a macroscopic force large enough to stop your hand cold. The table pushes back with a force exactly equal to the force you apply. It feels perfectly solid. It feels absolute. And it is at the macroscopic level. Even though at the atomic level, nothing solid is touching anything solid. This scaling up from quantum to macroscopic is what creates every material property you have ever experienced. The hardness of a surface, the flexibility of a wire, the brittleness of a ceramic, the smoothness of polished metal, the roughness of sandpaper. Every single one of these properties is a macroscopic manifestation of quantum rules governing electron behavior at the atomic level. Let me show you how this works with one of the most striking examples in all of chemistry. Take two objects. One is a diamond, one of the hardest natural substances known. The other is a piece of graphite, the soft, dark material in the core of a pencil. Both objects are made of exactly the same element, pure carbon. Every atom in the diamond is a carbon atom. Every atom in the graphite is a carbon atom. Same number of protons, same number of electrons, same nuclear structure, same electron cloud configuration for each individual atom. And yet, diamond is so hard that it can scratch almost any other material on Earth. Graphite is so soft that it leaves a dark smear on paper when you drag it across the surface. Diamond is transparent. Graphite is opaque and dark. Diamond is an electrical insulator. Graphite conducts electricity. How can the same atoms produce such wildly different materials? The answer is entirely about how the electron clouds of those carbon atoms interact with each other. It is about the bonds. In diamond, each carbon atom shares electrons with 4 neighboring carbon atoms through strong covalent bonds. A covalent bond forms when 2 atoms share electrons, creating a region of high electron density between their nuclei. This shared electron cloud pulls both nuclei toward the center, holding the atoms firmly together. In diamond, these 4 bonds point outward from each carbon atom in a perfectly symmetrical 3-dimensional arrangement, forming a tetrahedral shape. Each carbon atom is locked rigidly to 4 neighbors. Each of those neighbors is locked to 4 more. The pattern repeats throughout the entire crystal, creating a continuous 3-dimensional lattice where every atom is firmly bonded in every direction. To deform this lattice, to scratch the surface of the diamond or compress it or break a piece off, you would need to break covalent bonds. And covalent bonds between carbon atoms are extraordinarily strong because the electromagnetic interaction holding the shared electrons in place is intense. The shared electrons sit in a deep energy well between the 2 nuclei, and pulling them out of that well requires a great deal of energy. The exclusion principle also plays its role here. The electrons participating in each covalent bond are in specific quantum states dictated by the exclusion principle. They cannot simply shift to other states without absorbing or releasing precise amounts of energy. The bond structure is rigid because the quantum states are rigid. In graphite, each carbon atom also forms strong covalent bonds, but only with 3 neighbors instead of 4. These 3 bonds create flat sheets of carbon atoms arranged in hexagonal rings, like a honeycomb viewed from above. Within each sheet, the bonds are strong. The carbon atoms are locked together with the same ferocious covalent grip that makes diamond hard. But the 4th electron, the one that would form the 4th bond in diamond, does something different in graphite. It becomes delocalized. Instead of participating in a covalent bond to a 4th neighbor, it joins a cloud of mobile electrons that spreads across the entire sheet. These delocalized electrons are shared among all the atoms in the layer, not locked between specific pairs. This gives the individual sheets of graphite remarkable properties. But it also means the sheets interact with each other only through weak forces, not through covalent bonds. The flat hexagonal sheets are stacked on top of each other, but the interactions between layers are feeble compared to the bonds within each layer. The sheets can slide over one another with very little force. This is why graphite is soft. When you press a pencil against paper, the graphite layers slide apart at the weakest links, the gaps between sheets. Thin flakes of graphite peel off and stick to the paper fibers, leaving a dark mark. You have not broken any covalent bonds. You have simply separated layers that were barely holding onto each other in the first place. Same atoms, same element, same number of protons and electrons, completely different materials. The difference is entirely in how the electron clouds bond to each other, which bonds they form, which quantum states they occupy, and how the exclusion principle distributes the available electrons across the available states. Diamond and graphite are both built from carbon, but the quantum architecture of their electron interactions produces materials so different that one can scratch almost anything, and the other is used as a lubricant. This principle extends to every material you encounter. Metals feel the way they do because of a specific kind of electron behavior. In a metal like iron or copper, the outermost electrons of each atom are not bound tightly to their individual atoms. Instead, they become delocalized across the entire metallic crystal, forming what physicists call an electron sea, or electron gas. The positively charged nuclei sit in a regular lattice, immersed in this shared pool of mobile electrons. The metallic bond, the force holding the metal together, arises from the electromagnetic attraction between the positively charged nuclei and the negatively charged electron C. Each nucleus is attracted to the electron C surrounding it, and since the electron C is shared by all the nuclei, the entire structure is bound together. This delocalized electron structure explains every familiar property of metals. Metals conduct electricity because the mobile electrons can flow through the lattice in response to an applied voltage. Metals conduct heat well because the mobile electrons can carry thermal energy rapidly from hot regions to cold regions. Metals are shiny because the mobile electrons can absorb incoming photons and re-emit them, reflecting light efficiently. Metals can be bent and hammered into shapes because when the lattice layers shift, the electron C simply adjusts. The electromagnetic interaction between the nuclei and the shared electrons is maintained regardless of the exact arrangement of atoms, so the bond does not break when the material is deformed. This is why you can bend a copper wire without it snapping. The atoms shift positions within the lattice, layers slide over each other, but the electron C accommodates the change. The electromagnetic interactions are maintained in the new configuration. The metal has been reshaped, not broken. Compare this to a ceramic or a piece of glass. In these materials, the bonds between atoms are rigid and directional. Each atom is locked to specific neighbors through bonds that point in precise directions. The electrons participating in these bonds are not free to move. They are trapped in specific quantum states between specific pairs of atoms. When you apply force, there is no flexible electron C to accommodate the deformation. The bonds either hold or they snap. And when they snap, the material cracks. A ceramic plate dropped on a hard floor shatters because its electron bonding structure has no mechanism for gradual adjustment. The bonds break, the crack propagates through the lattice, and the material falls apart. Glass is an interesting variation. Its atoms are not arranged in a regular crystalline lattice. They are frozen in a disordered arrangement, an amorphous solid. But the bonds between atoms are still rigid and directional. Glass can withstand compression and moderate tension, but a sharp impact concentrates force at a point, breaking bonds locally and initiating a crack that spreads through the material at incredible speed. Glass shatters explosively because once a crack begins, the stress at the crack tip is amplified, breaking more bonds, extending the crack, breaking more bonds, in a runaway chain reaction that takes the material apart in milliseconds. Rubber behaves differently from both metals and ceramics because of yet another electron configuration. Rubber is made of long-chain polymer molecules, carbon atoms linked together in sequences thousands of atoms long, with hydrogen atoms attached along the sides. The covalent bonds within each chain are strong. The chains themselves are nearly indestructible under normal conditions. But the chains are loosely tangled and connected to each other through weak bonds at scattered cross-link points. When you stretch rubber, you are not breaking bonds. You are straightening the tangled chains, pulling them into alignment. The chains resist because straightening them reduces their entropy, the disorder of the system, and thermodynamics pushes back against reduced entropy. When you release the rubber, the chains retangle, the entropy increases, and the rubber snaps back to its original shape. The elasticity of rubber is a macroscopic consequence of how polymer chains are arranged and how the electrons bonding those chains interact. Even something as simple as the difference between a hard material and a soft material comes down to the quantum arrangement of electrons. Lead, the metal, is soft. You can scratch it with a fingernail. Iron is hard. Both are metals. Both have delocalized electron Cs. Both have crystalline lattice structures. So why is lead so much softer than iron? Part of the answer lies in the strength of the metallic bonds, which depends on how many electrons each atom contributes to the electron C and how strongly the nuclei attract those electrons. Iron has stronger metallic bonds than lead. Its electron configuration creates a deeper energy well for the shared electrons, making the lattice harder to deform. Lead has weaker metallic bonds. Its electron configuration produces a shallower energy well, so the lattice layers slide over each other more easily. Another part of the answer involves crystal structure. The way atoms are arranged in 3 dimensions affects how easily layers can slide. Some arrangements have natural slip planes where layers can shift with minimal resistance. Others have geometries that interlock, making sliding more difficult. The crystal structure of a metal is determined by the quantum states available to its electrons, which are determined by the exclusion principle. The Pauli exclusion principle, a rule about individual electrons, ends up determining whether a metal bar bends easily or resists deformation. There is another category of material that reveals the power of quantum states in an especially dramatic way, one that has reshaped the entire modern world: semiconductors. A semiconductor like silicon sits in a peculiar middle ground between metals and insulators. In a metal, electrons are free to move throughout the lattice. In an insulator like glass or rubber, electrons are locked in place, bound tightly into specific bonds with no freedom to roam. A semiconductor is neither. Its electrons are not free at room temperature, but they are not hopelessly trapped either. They sit in a state of readiness, almost free, needing just a small push of energy to become mobile. The reason for this behavior lies in the quantum energy levels available to the electrons, arranged into what physicists call bands. In any crystalline solid, the energy levels available to electrons are not scattered randomly. They cluster into bands of allowed energies separated by gaps of forbidden energies. These gaps are called band gaps, and their size determines whether a material conducts electricity or not. In a metal, the highest occupied energy band is only partially filled. Electrons at the top of this band can easily move into empty states just above them. There is no gap to cross. They can flow freely, carrying electrical current. This is why metals conduct. In an insulator, the highest occupied band is completely full, and the next available band is separated by a large energy gap, typically several electron volts or more. No electron in the filled band has enough energy to jump across the gap into the empty band above. The electrons are stuck. They cannot move. No current flows. This is why rubber and glass are insulators. In a semiconductor like silicon, the highest occupied band is also completely full, but the gap to the next available band is small, typically about 1 electron volt for silicon. At low temperatures, the electrons cannot cross even this small gap, and silicon behaves like an insulator. But at room temperature, thermal energy, the random jiggling of atoms, provides just enough energy for a small number of electrons to jump across the gap into the empty band above. Once in this upper band, called the conduction band, the electrons are free to move. They can carry current. Silicon becomes a weak conductor. This is remarkable enough, but the truly revolutionary insight was that you can control how many electrons cross the gap by adding tiny amounts of other elements to the silicon crystal. This is called doping. Add a trace of phosphorus, which has one more outer electron than silicon, and you introduce extra electrons that sit just below the conduction band. These electrons need almost no energy to jump up and become mobile. The material becomes a much better conductor. Add a trace of boron, which has one fewer outer electron than silicon, and you create holes, empty spots in the filled band that other electrons can hop into. The holes behave like mobile positive charges, also carrying current. By combining regions doped with different elements, engineers build transistors. the switches that form the basis of all modern electronics. A transistor is a device whose conductivity can be turned on and off by applying a small voltage. It is a quantum switch. Its operation depends entirely on the band gap of the semiconductor, which depends entirely on the quantum energy levels available to the electrons, which depend entirely on the exclusion principle governing how electrons fill those levels. Every computer chip, every smartphone processor, every LED light, every solar panel is built from semiconductor materials whose properties are dictated by quantum mechanics at the atomic level. The exclusion principle determines which energy levels are filled. The band structure determines whether electrons can move. The band gap determines whether the material is an insulator, a semiconductor, or a conductor. The entire digital revolution, every piece of technology that defines modern life, is a macroscopic consequence of the Pauli exclusion principle operating in crystals of silicon. The quantum origin of material properties becomes even more fascinating when you look at biological materials, because living systems have discovered ways to combine different bonding strategies within a single structure to create materials with properties that no simple crystal or metal can match. Consider bone. Your skeleton is not made of a single uniform substance. It is a composite, an intricate combination of two very different materials woven together at the microscopic level. The first component is a mineral called hydroxyapatite, a crystalline arrangement of calcium, phosphorus, oxygen, and hydrogen atoms locked into rigid ionic and covalent bonds. Hydroxyapatite by itself is hard and stiff, like a ceramic. It resists compression well, but is brittle. A block of pure hydroxyapatite would shatter under impact, just like glass. The second component is collagen, a protein made of long, flexible chains of amino acids twisted into a triple helix structure. Collagen by itself is tough and flexible, but soft. It bends and stretches easily. It resists tension well, but has almost no rigidity. Bone combines these two materials at the nanometer scale. Tiny crystals of hydroxyapatite are embedded within and between collagen fibers, creating a structure that is both hard and tough. The mineral provides rigidity and compressive strength. The collagen provides flexibility and tensile strength. Together, they create a material that can support enormous loads without shattering, that can absorb impacts by flexing slightly rather than cracking, and that can heal itself when damaged because living bone cells continuously remodel the composite structure. This is a quantum engineering triumph achieved by evolution over hundreds of millions of years. The hardness of the mineral crystals comes from the rigid electromagnetic bonds between their ions. The flexibility of the collagen comes from the way its long polymer chains can straighten and coil, absorbing energy through conformational changes. The composite structure exploits both bonding strategies simultaneously, combining the strengths of each while compensating for the weaknesses of the other. Similar principles appear throughout the biological world. Seashells contain a material called nacre, or mother of pearl, which is made of microscopic tablets of aragonite, a crystalline form of calcium carbonate, layered between thin sheets of organic polymer. This structure is thousands of times more fracture-resistant than pure aragonite, because the organic layers deflect cracks, forcing them to follow a tortuous path that absorbs enormous amounts of energy. Spider silk combines rigid crystalline regions of tightly bonded protein with flexible amorphous regions of loosely coiled chains. The rigid regions provide strength. The flexible regions provide extensibility. The result is a fiber that, weight for weight, is stronger than steel and can stretch up to 30% or more of its length before breaking without snapping. Wood is another remarkable example. Its strength comes from cellulose fibers, long chains of glucose molecules bonded together by strong covalent bonds. These fibers are embedded in a matrix of lignin, a complex polymer that provides rigidity. The cellulose fibers resist tension, the lignin resists compression. Together, they create a material strong enough to support a tree hundreds of feet tall against the force of gravity and the stress of wind, flexible enough to bend without breaking in a storm, and light enough to be carried by a single person when cut into lumber. Keratin, the protein that makes up your hair and fingernails, uses yet another strategy. Its molecules form long helical chains that are cross-linked by chemical bonds between sulfur atoms. The density of crosslinks determines the material's stiffness. Hair has relatively few crosslinks and is flexible. Fingernails have more crosslinks and are rigid. Rhinoceros horn has a very dense network of crosslinks and is extremely hard. Same protein, same amino acids, same electron configurations at the single molecule level. The macroscopic properties change because the quantum bonding architecture changes. In every case, the material properties of biological structures trace directly back to how electrons are arranged in quantum states, how those electrons form bonds, and how the Pauli exclusion principle determines which energy levels are occupied and which configurations are stable. Biology did not invent new physics. It discovered, through billions of years of natural selection, extraordinarily sophisticated ways to arrange the same quantum building blocks that make up everything else in the universe. The lesson is profound. The quantum world is not a separate realm disconnected from the world you experience. It is the world you experience. Every texture you feel, every color you see, every material you interact with, is a macroscopic expression of quantum rules operating at scales far below your senses. The hardness of the sidewalk under your shoes is quantum mechanics. The flexibility of the shirt on your back is quantum mechanics. The rigidity of the bones inside your body is quantum mechanics. The transparency of the air you are looking through right now is quantum mechanics. There is no boundary where the quantum world ends and the everyday world begins. They are the same world, observed at different scales. This cascade from quantum rules to macroscopic properties is one of the most beautiful things in physics. A rule that governs individual subatomic particles stated in a single sentence: no two identical fermions can occupy the same quantum state, ripples upward through scale after scale of organization, from electrons to atoms to bonds to crystal structures to materials to objects you hold in your hand, ultimately determining whether that object is hard or soft, rigid or flexible, transparent or opaque, conductive or insulating. And every moment of your life, you are interacting with this cascade. When you walk across a wooden floor, the firmness you feel underfoot comes from cellulose fibers made of glucose molecules, made of carbon, hydrogen, and oxygen atoms whose electron clouds are locked in covalent bonds arranged in rigid chains. When you hold a metal spoon, the coolness you feel is heat flowing from your skin into the metal, conducted rapidly by delocalized electrons in the metallic lattice. When you look through a glass window, photons of visible light pass through because the electrons in the glass atoms have energy gaps between their quantum states that are larger than the energy of visible photons, so visible light is not absorbed. When you see the blue sky, you are seeing sunlight scattered by interactions between photons and the electron clouds of nitrogen and oxygen molecules in the atmosphere. All of it comes back to electrons, their quantum states, their electromagnetic interactions, their absolute obedience to the Pauli exclusion principle. The world you see, touch, and feel is a world built from quantum rules playing out simultaneously across trillions upon trillions of atoms. And this brings us to a realization that is both strange and beautiful. You have never touched anything, not in the way you intuitively believe you have. When you feel the smooth surface of a polished table, what you are actually feeling is the electromagnetic force between the electron clouds on your fingertips and the electron clouds on the table's surface. The nuclei of your finger atoms and the nuclei of the table atoms are never in contact. They are separated by the width of overlapping electron clouds, a distance of a few angstroms at most. That gap is maintained by electromagnetic repulsion and the exclusion principle. Your nerves detect the forces generated by this electromagnetic interaction, and your brain interprets those forces as the sensation of touch. The sensation is real, the forces are real, but physical contact in the classical sense, atom pressing against atom like two billiard balls meeting, never occurs. Every handshake you have ever shared was an electromagnetic event between two separate clouds of quantum probability. Every kiss was an interaction between electron distributions obeying the exclusion principle. Every time you have held a child in your arms, your atoms and their atoms were separated by an electromagnetic boundary that neither set of atoms crossed. The warmth you felt was infrared radiation and heat conduction, energy transferred through electromagnetic interactions and molecular vibration, not through contact between solid objects at the deepest level. Now, you might hear all of this and conclude that solidity is an illusion, that the table is not really solid, that the ground is not really firm, that everything you have ever felt was somehow fake, a trick your senses play on you because you cannot perceive atoms. But that conclusion would be wrong. Solidity is not an illusion. It is an emergent property, and emergent properties are every bit as real as the things they emerge from. Temperature is not an illusion just because individual atoms do not have a temperature. Wetness is not an illusion just because a single water molecule is not wet. These are properties that exist at one scale and not at another, but their existence at that scale is genuine, measurable, and physically consequential. Solidity works the same way. It does not exist at the level of a single atom, but it absolutely exists at the level of trillions of atoms interacting through quantum rules. The table holds your coffee cup, the floor holds your weight. These are real physical facts. Solidity is real. It is simply not what you thought it was. This is not a limitation. It is not a deficiency. It is simply what touch actually is when you look closely enough. The human experience of contact, of texture, of pressure, of warmth is a macroscopic interpretation of quantum electromagnetic interactions happening at scales billions of times smaller than the tip of your finger. Your nervous system evolved to detect these forces and report them as sensations. Your brain learned to interpret those sensations as solid, soft, rough, smooth, warm, cold. These interpretations are extraordinarily useful. They let you navigate the world, handle objects, build tools, comfort other people. But beneath the interpretation, beneath the sensation, beneath the everyday experience, lies a quantum reality where solidity is not a property of matter itself, but an emergent consequence of how electron clouds interact. Matter does not push back because it is made of hard stuff. It pushes back because its electrons obey rules that create effective rigidity at the atomic scale. Hardness is not a thing, it is a behavior. It is what electrons do when they are organized in certain patterns and governed by certain principles. This makes the everyday world more remarkable, not less. You are surrounded by objects whose solidity, texture, color, and structure arise entirely from the quantum behavior of particles so small that no human eye will ever see them directly. The floor beneath you is held rigid by quantum statistics. The light illuminating your room is emitted and absorbed through quantum transitions between electron energy levels. The screen you are seeing these words on is displaying information through electromagnetic interactions between electrons in its materials and photons reaching your eyes. You are a quantum being living in a quantum world, using a brain made of atoms to understand the atoms you are made of. Every thought you have is a pattern of electrical and chemical activity in your neurons, driven by ions crossing cell membranes through protein channels, powered by molecular energy carriers, all of it ultimately governed by the electromagnetic force and the exclusion principle operating at the atomic level. And the apparent simplicity of your everyday experience, the effortless sensation of sitting in a chair and feeling it hold your weight, conceals an ocean of quantum complexity. Trillions of atoms interacting through electromagnetic forces. Electrons distributed across quantum states according to the exclusion principle. Covalent bonds, metallic bonds, ionic bonds, van der Waals interactions, hydrogen bonds, all different manifestations of the same underlying electromagnetic force, filtered through different quantum configurations of electrons. All of it adding up, at the macroscopic scale, to the single, simple sensation. This is solid. This holds me up. This resists my push. The ancient Greeks debated whether matter could be divided forever. 2,400 years later, we know the answer. Matter is made of atoms. Atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks and gluons. At each level, there are building blocks and there are rules. And the rules at the quantum level, especially the electromagnetic force and the Pauli exclusion principle, are what create the tangible physical reality you inhabit every moment of your life. The atom is almost entirely empty by volume. Its nucleus is 100,000 times smaller than the full atom, yet contains virtually all the mass. The electron cloud, a quantum probability distribution with no hard edges and no solid walls, defines the atom's apparent size and governs all of its external interactions. When atoms approach each other, their negatively charged electron clouds repel through the electromagnetic force, and the exclusion principle prevents electrons from collapsing into shared low-energy states, creating a fundamental structural rigidity that resists compression. Together, these two mechanisms produce solidity. Not because matter is made of tiny hard balls, not because atoms have rigid shells, not because nuclei physically touch each other across the gaps between atoms. Solidity arises because quantum rules governing the behavior of electrons create effective resistance to compression at the atomic scale, and because trillions upon trillions of these tiny quantum interactions, acting in concert, produce macroscopic forces large enough to hold up your body, large enough to support buildings, and, in the extreme case of a white dwarf star, large enough to hold up the mass of an entire dead sun against the crushing force of gravity. The world feels solid because of quantum mechanics. The floor holds your weight because of quantum mechanics. The table resists your hand because of quantum mechanics. Every texture, every surface, every material property you have ever experienced is a consequence of how electrons are arranged in quantum states and how they interact through the electromagnetic force, all governed by a rule stated in a single sentence by Wolfgang Pauli almost exactly a century ago. You live inside this reality every moment of every day. You walk on it, you breathe it, you hold it in your hands. The tangible, textured, resistant physical world, the world of solid ground and firm walls and hard edges and soft fabrics, is built entirely from quantum rules operating at scales far too small to see, producing the magnificent reality of solidity from particles that are not solid, structures that have no hard edges, and atoms that are overwhelmingly, beautifully, almost perfectly empty.